this presentation, we're going to look at a worked example of the Rayleigh distribution. So this comes up in modules related to probability distributions, more advanced ones that you might sort of see in third and fourth year engineering courses and science courses. Okay, just a quick example of the Rayleigh distribution. This distribution is often used to model the magnitude of a two-dimensional vector whose components are independent and normally distributed with mean zero and equal variance. So essentially, x describes the x distance, the horizontal displacement from the origin, and it's a random variable, a normal random variable. Likewise, y is a normal random variable that describes the vertical displacement from the origin. Essentially, the Rayleigh random variable is the magnitude of a point that is described by x and y, and the distance from the origin, the real distance from the origin. Okay, so we'll leave that for another time. So, the example, wind speed analysis. Suppose we are now analyzing wind speeds in a particular region. The wind speed v can be modeled using the Rayleigh distribution with a scale parameter sigma. Okay, let's assume that sigma equals 3 meters per second. So here we have four little exercises. The first one is state the probability density function PDF for v. The second one is state the cumulative distribution function CDF for v. Calculate the probability that the wind speed is between 2 meters per second and 5 meters per second. And then state the expected value and variance of v. So it's a straightforward enough one, really. Okay. So exercise 1, probability density function. So this is what you would see in a book. This is the first line here. The CDF of the Rayleigh distribution is given by as follows. So small lowercase f, that describes that's the notation for the probability density function. X is just to actually sort of emphasize that this, until you're told otherwise, usually a random variable is denoted x, and we express things in terms of x. So in this case, it would be the arguments would be x and sigma, which is the scale parameter, and that is equal to x divided by sigma squared times the exponential of minus x squared divided by 2 sigma squared, where x is greater than or equal to 0. Just what we have to do here to get the proper answer is actually rearrange that. Okay, and re-express it in terms of v, because we were actually told that the v is the random variable that describes wind speed. So essentially what we have to do is just re-express the probability density function in terms of v. So we have f of v, so you see that subscript v there, lowercase f, subscript v, capital V. Okay, just to sort of, because we were told that. V of v and 3, so the realization, the notation for the realization is v, and the scale parameter is 3. Okay, for scale parameter, sigma is equal to 3. What we have there is v divided by 9, which is sigma squared is 3 squared, so 9, v divided by 9, times the exponential of minus v squared divided by 18, for v greater than or equal to 0. Okay. Just watch out for those little banana skins there. So just actually, this should be a straightforward enough question, but not only do you have to specify the probability density function with sigma equals 3 and evaluate it as such, you have to just actually specify it in terms of v, and also don't forget these little terms here, v greater than or equal to 0. Okay, I'm going to skip past that from now on. Actually, I'm going to move past that. So everything I've just said there applies to subsequent questions, even though I probably won't mention it as much. So the cumulative distribution function, sorry, that should say CDF there, it's a little typo. Anyway, the cumulative distribution function is as follows, where x is greater than or equal to 0. So capital F of x, so just actually remember that capital F is the notation for the CDF, the density function. Okay, x and sigma are the arguments there, and that is equal to 1 minus the exponential of minus sigma squared divided by 2 sigma squared. Okay, so again, we do something similar here. Sigma is equal to 3, and what we do is express it in terms of v. So capital F subscript capital V. Okay, that's just to say the cumulative distribution function of a variable called v. V and 3, sigma equals 3, and that's equal to 1 minus the exponential of minus v squared divided by 18 for v greater than or equal to 0. Okay, and again that should be CDF. That's my little mistake there. Anyway, we'll keep moving. Okay, so the probability interval. What we have to do here is calculate the probability that the wind speed is between 2 meters a second and 5 meters a second. So the probability of 2 being less than or equal to v less than or equal to 5. So just rearranging that, what we would say is the probability of v less than or equal to 5 minus the probability of v less than or equal to 2. And just recall the cumulative distribution function of v. Okay, I'm just stepping back a bit with the specifications. I'm just trying to keep it simple here. So f of v and 3 is equal to 1 minus the exponential of minus v squared divided by 18. Okay, so the probability of v less than or equal to 5, that is equal to the cumulative distribution of 5 with scale parameter sigma equal 3. And likewise, probability of v less than or equal to 2, that is equal to the cumulative distribution of 2 where the scale parameter is 3. This last bit actually is just really just specify the relationship between the probabilities and the cumulative distribution functions. This probably is something you probably already aware of and think this might be a bit unnecessary, but sometimes, it doesn't. It's no harm to just emphasize this sort of stuff. Okay, so what we have to do here is calculate f of 5 and f of 2, where the scale parameter is 3 in both cases. So f of 5 is equal to 1 minus the exponential of minus 25 divided by 18. So v is 5, v squared is 25. Okay, a little bit of calculator work. That is approximately equal to 1 minus the exponential of minus 1.39. Working that out, the exponential of minus 1.39 is 0.249. So 1 minus 0.249, that is approximately 0.751. So 75% essentially. And what we do here is something similar for f of 2. So v equal to 2. So v squared is equal to 4. Okay, so that's the only real difference in this expression here. 1 minus the exponential of minus 4 divided by 18. That's approximately equal to 1 minus the exponential of minus 0.22. That is approximately equal to 1 minus 0.802, and that is equal to 0.198. So essentially, the difference between the two gives us the probability of the wind speed being between 2 meters a second and 5 meters a second. So the probability of v being between 2 and 5 is the f of 5 minus f of 2, where in both cases the scale parameter is 3. And we have approximately 0.751 minus 0.198. So working that out, that works out to be 0.553. So approximately 55.3% chance that the wind speed is between 2 meters a second and 5 meters a second. So we're moving on. Okay. So state the expected value and variance. So the mean, which is the expected value, capital E of v, and the variance, VAR of v, or VAR of v, of the Rayleigh distribution are given as follows. So expected value of v equals sigma times the square root of pi divided by 2, and the variance is 2 minus pi over 2 times sigma squared. So putting in sigma equal to 3, we get the expected value is 3 times the square root of pi divided by 2. That is approximately 3 times 1.253. So that works out to be 3.759 meters per second. And the variance, 2 minus pi divided by 2 times 9, that is 0.429 times 9. and that is approximately 3.861 meters squared per second squared. If you pardon my verbalization of that term there. Okay, so there we have it there. The PDF is v over 9 times the exponential of minus v squared divided by 18. Cumulative distribution function is 1 minus the exponential of minus v squared divided by 18. The probability of the wind speed being between 2 meters per second and 5 meters per second is 55.3%. The mean is approximately 3.759 meters per second, and the wind speed is, little typo there, but it is 3.861 meters per second to be squared. Okay, we'll leave it there.